In this question, we'll be looking for 4 three-digit numbers to put in that are clued in the question. Now, as a starting point, it's useful to start with the clue that restricts our choices as much as possible. There are a large number of multiples of 9, multiples of 11, and indeed squares that fit the three-digit criterion. However, there will be far fewer options for three-digit multiples of both 13 and 19. 13 and 19 are both prime numbers, so for a number to be a multiple of both 13 and 19, it actually needs to be a multiple of the product of 13 and 19, which is 247. We can look at the multiples, 247 times 2, times 3, and times 4. This is the last one that still fits in 3 digits. The next one will be larger than 1,000, and so would no longer fit in this grid. So this is the right-hand column. We know one of these numbers needs to go into the right-hand column. We know that there are no repeat digits in our grid, and therefore we can cross out options that repeat digits. Because this features 2 4s and this features 2 8s. We can now look at the clue for the bottom row, which says that it has to be a square. Now, can a square end in 7? The answer is no. Let's explore why. The last digit of a square, or indeed the product of any numbers, is only determined by the last digit. 1 squared ends in 1. 2 squared ends in 4. 3 squared ends in 9. 4 squared ends in 6. 5 squared ends in 5. 6 squared ends in 6. 7 squared ends in 9. 8 squared ends in 4. And 9 squared ends in 1. 0 squared ends in 0, which is not a possibility here anyway. I can just write it down. But we can see that 7 is not a possible last digit. The only possible last digits for a square number are 1, 4, 9, 6, 5, and 0. Therefore, we can eliminate 247 from consideration. And we can put in 741 in our right-hand column. We saw just now that in order for a square to end in the digit 1, the number that's being squared had to end in 1 or in 9. In the other cases, we were getting squares ending in digits other than 1. We now need to consider which square numbers will end in the digit 1. So we will start with 11 squared, which gives us 121, knowing that 10 squared is 100 and all smaller squares will have fewer than 3 digits. And we'll have to work up to 31 squared, going through the possibilities that end in 1 or 9. So we'll go 11 squared, 19 squared, 21 squared, 29 squared, and 31 squared. Beyond that, 39 squared ends up being greater than 1,000 and so will no longer fit in 3 digits. These are the possible square numbers, therefore, that could go in this bottom row. However, not all of them actually fit with the criteria of the question. In particular, we once again can cross out those that repeat digits, because this contains 2 1s and this contains 2 4s. We can actually also get rid of 841 because we can't reuse the 4 that we've already used over here. So we're left with 2 possibilities for the number that goes in the bottom row, both of which have 6 as the middle digit, so we might as well put that in now. If we look at the next clue, we know that in the top row, we have a number that's divisible by 9. Now, our criterion for divisibility by 9 is that the digit sum is divisible by 9. These two digits, alongside 7, have to add up to a multiple of 9. The smallest possibility we could consider is that they add up to 9. However, then both of them would have to equal 1, and we don't want to repeat the same digit. Therefore, we need the sum to be at least 18. In fact, it has to be exactly 18, because after 18, the next multiple of 9 is 27. If we subtract the 7, we would need these two digits to add up to 20, but of course that's impossible with digits that only go up to 9. Therefore, we know that this sum is going to be exactly 18, so the sum of these two digits is going to be exactly 11. There are multiple ways in which two digits can add up to 11, but we've already eliminated some of the possibilities by having used certain digits. In fact, the only possibilities for the digits here will be 29, 38, 83, or 92, because we cannot have 4 again, because we've used it already, and we cannot have 6 again. So 4 plus 7, even though it does add up to 11, we cannot use anymore, and neither can we use 5 plus 6 in either order. If we now think about what this means for the rest of this grid, we've only got 2 possibilities for the bottom row, but each time we use one of the possibilities, we actually eliminate 2 of the options, because if we use 3, 6, 1, we cannot use 3 in our top row, and if we use 9, 6, 1, we cannot use 9 in the top row. Therefore, we only have 4 possibilities that we can now systematically work through. Let's work through this trial version. If we insert 2 and 9 in the top row and 3 in the bottom row, and we want to make the number in the left column divisible by 11, let's remind ourselves about how to check whether a number is divisible by 11. You need to use the alternating digit sum in this case. So we add together 2 and 3, and we subtract the middle digit. Now 2 plus 3 is 5, and so if we insert a 5, this number, 253, will be divisible by 11, and this is a valid grid. Now we can check which of the digits 1 to 9 is missing, and it is 8. The option 8 is therefore correct. For completeness, we should go through all the other options and find out that we cannot complete the grid successfully, because the digit that needs to be inserted in this position in order to make the left-hand column divisible by 11 is actually a repeat of a digit that is already in the grid.